studying potentiometers. So, we have studied DC and AC potentiometers, and in this context another equipment often becomes very useful, which is a potential divider. In this class we will see what a potential divider is. We will take a small example in the context of potentiometer to understand why a potential divider can be useful, and then finally we will study Kelvin-Varley potential divider, which is the focus of this class. Okay. So, let us start this class with the question, when we may need a potential divider. So, the answer we can see with an example. And the example is as follows: we want to measure a voltage which is about say 100 volt. So, we want to measure it using a potential divider, using a potentiometer. And we have a standard cell with EMF E is equal to 1.08 something. Okay. So, let us take it for ease of calculation, let us take it to be 1 volt only. Okay. So, let us take it 1 volt for ease of calculation now. Now, suppose the length of the potentiometer is 11 meter. Say this length is 11 meter. Okay. Now, so we want to measure 100 volt and something around 100 volt. It is only possible if the voltage between the 2 points of this wire is greater than the unknown voltage, which is 100 volt. So, therefore, we definitely need a supply, DC supply, which will provide more than 100 volt here. So, if I take this side as the reference 0 volt, this side should be around maybe 110 volt. Okay. That is a easy number. So, if I choose to have 110 volt here, this will imply, so 11 meter is equal to 110 volt. So, we can write, so 11,000 millimeter is equal to 110 volt. So, 1 millimeter will be 1 over 100 volt, right. Okay. Yeah, 1 over 100 volt, this will be equal to 1 millimeter. Now, so 1 volt will be how much? So, 1 volt will be therefore equivalent to, so divide this by 110, we will have 100 millimeter, which is like 10 centimeter. Okay. Now, so therefore, for calibration we have to set the jockey of the standard cell. So, this is the standard cell, minus side plus side, this has to be consistent, minus and plus. So, let this be the galvanometer. So, you have to set the jockey somewhere around 10 centimeter, exactly at 10 centimeter, and then adjust this current to get the null. Now, if we make a mistake, instead of setting it to say 10 centimeter, say if we set it to 10 centimeter plus minus 1 millimeter, so that is a mistake. So, if by mistake we put the this jockey during calibration, jockey at, so it should be at 100 millimeter, say we put it at by mistake say 102 millimeter. Okay. So, we have a 2 millimeter mistake during calibration, which means 2% error. Okay. So, why 2%? Basically, now, so we wanted that 100 millimeter equal to 1 volt, but we have so let me write it this way. So, we wanted 1 millimeter equal to 1 by 100 volt, and we actually have 1 millimeter equal to 1 over 102 volt. So, we have a, so now this is a 2% error approximately. If you remember the rule for error in product and division, then you know that this is approximately a 2% error in the voltage per millimeter. Therefore, during the measurement, okay, so if we get the balance, so this is the Vx unknown, if we get the balance somewhere here at 10 meter, okay, then we will estimate Vx as, so Vx estimated will be, actually 10 meter means 10 by 11 into 110 volt. So, this will be 100 volt. So, this is Vx estimated, but Vx true will be Vx true, this will be how much? This will be 100, so this will be, so we have the null at 10 meter, 10 meter means 10,000 millimeter, and 1 millimeter is equivalent to 1 over 102. So, this much volt, so which will be less than 100 volt, okay, and the error will be approximately 2% or minus 2%. Okay. This is because we are setting, I mean we have the full length equal to 110 volt, and so 1 volt is within a very small distance, and we can make a mistake, okay, in setting this jockey instead of at 100 millimeter, we may set it at 102 millimeter. So, that is the mistake, and the mistake will be more severe, say if we want to measure a voltage which is around 1000 volt. Okay. So, if that was the case, so now if we want to measure, just let us do the calculation very quickly. Now, if we want to measure say something around 1000 volt, okay. So, I am increasing the value of the voltage that I want to measure, but the standard cell is still it has the same EMF 1 volt, because standard cell voltage is not going to change. Okay. So, then we have to set this point somewhere around 1100 volt, and then we should do the calibration by putting the jockey at 1 centimeter. Okay. So, this is like now 1 centimeter will be equivalent to 1 volt. So, now 1 centimeter is 10 millimeter, and while setting the jockey, if we make say 2 millimeter mistake, if the jockey is put at say 12 millimeter by mistake, by manual error or due to the error in the scale, whatever the reason is, then we will have 20% error. So, we will finally have 20% error in the measured voltage. So, that is the problem. Now, there is a solution. Okay. So, the problem is we may have low accuracy, and now the solution to this problem is as follows. If this is 1000 volt, instead of measuring this voltage directly with a potentiometer, what we can do, we will use something called a potential divider. Okay, and we will give this input Vx, which is 1000 volt. So, we will give Vx as the input to this potential divider, and the function of the potential divider is to divide the input by some factor. Say this divides by a factor of 1000. Okay. So, then we will have output which is around 1 volt. If this is around 1000 volt, output will be around 1 volt, and this voltage we will apply to this potentiometer. So, that is one side, another side goes like this. Okay. And so, the voltage that we are actually measuring is 1 volt. We are not measuring 1000 volt, we are measuring a much smaller voltage. Therefore, we can choose to set this side to have something around 1.1 volt, that is enough. Okay. And if we choose so, if 11 meter or 11,000 millimeter if we choose it to be 1.1 volt, then for calibration jockey should be at 1 volt, because this is 1 volt standard cell. So, jockey should be at 1 volt, which means 1 volt is equivalent to, from this you can find this will be 1 meter or 1000 millimeter. Okay. So, we have to put the jockey somewhere down here at a distance of 1 meter or 1000 millimeter from the left side. Now, once again if we make some small mistake, say 2 millimeter mistake. So, if there is a 2 millimeter mistake, now this will imply how much error? 2 millimeter over 1000 millimeter. So, this is equivalent to 0.2%, which is much lower than the previous two cases, where we had either 2% error or 20% error. Okay. So, we can have much smaller error if we use a potential divider. So, the solution is to use a potential divider. And let me recap what a potential divider is. A potential divider is lower, it brings down this input voltage to a lower value. So, potential divider brings down the input voltage by some precise factor. It has to be precise. Okay. So, it is like output is equal to input divided by some factor, and this factor has to be precise. If we want to divide it by 1000, we should divide exactly by 1000, it should not be 1001. Then of course, there will be some error due to that, which we have not considered in this example. So, this may also have some error which can increase this estimated error. Okay. So, that we have not discussed. We have assumed this potential divider to be ideal. Okay. But in any, just a small note, even say if this is 1001 by an error, so that means it will cause 0.1% error, and so that is not as large as 2% or 20% in the previous example. So, this error can still be small depending on how good this potential divider is. Plus minus signs are important. Okay. Okay. Yes. So, now let us see how a potential divider can be made. Okay. So, let us now see circuit of potential divider. We have already seen why is it useful. So, this is basically a resistive divider. It's very simple. So, it's a set of resistances connected in series. So, 1, 2, 3, 4, let me take say 10, 5, 6, 7, 8, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And say if all these resistances are equal, we need this to be equal. And if we now apply a voltage here, say call it V in, this is the input voltage, and if we take the output, or if we measure the output between say these two terminals, then we have actually V out is equal to, in this case, V out will be same as 1, 2, 3, 4, 5, 5R divided by 10R multiplied by V in. So, this is V in by, so it is like 0.5 times V in. Now, we can move this jockey up or down, we can connect it here, 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 here or anywhere. So, accordingly we can get V out, which is a fraction of V in. So, with this circuit we can get any fraction of the input, which is like 0.1 times, 0.2 times, 0.3 times or 0.7, 8, 0.9. So, any fractions like that of this V in we can get with this circuit. Now, suppose we want to get V out is equal to say 1.1 times V in. So, sorry, 0.11 times V in. How is that possible? That is possible if we have say 100 such resistances R, okay, and then if we take the output from the 11th position. Okay. So, it is possible if we have 100 resistances and if we take the output after the 11th resistance. So, count 1, 2, 3, 4, so on, 11 resistances, total 100 resistances are there, count 11 and then put the jockey there, then you can get the exactly 0.11 of V in. Okay. So, output after 11th resistance. But then okay, you need 100 resistances and 100 equal resistances, they should be as equal as possible. This chain is becoming longer. Now, if I need V in to be say 0.123 up to 3 decimal places, then that means I need 1000 resistances. For 4 decimal place division, we need 10,000 resistances. It is very clumsy and not a good idea. So, another solution is okay, connect potential dividers in cascade. Okay, like this. So, let this be one potential divider and say this is the input V in, and say if we want V out to be equal to say 0.01 of V in. Okay. Then we can take two potential dividers, so this will divide by a factor 10, this will divide again by a factor 10. The output of this potential divider will feed to the input of the second one. So, this voltage will be 0.1 times V in, and then here we will get 0.1 times V in. Uh, 0.01. Okay. So, this is a solution. Now, how to make this cascade using this potential divider. So, let us try that. So, let me draw two potential dividers with 10 resistances 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3, 4, 5, 6, 7, 8, 9, 10. Okay. And so, this is one potential divider, this side is the input V in, and V out is between this terminal. You can take this as the reference for all measurement. So, V out will be between this and wherever you connect it. Okay. So, if you want to divide by a factor of 10, then you have to connect it here after the first resistance. Then let us make another one. Okay. Now, if I want to divide by a factor of 100, so this is dividing by a factor of 10. Now, this is also dividing by a factor of 10. So, what I can do? I can do it like this. So, I will connect, this is here, I will bring this output here, I will connect this, and I will take the final V out from here. So, this is the V out. So, this is like 1 over 10 and this is like another 1 over 10, which means 1 over 100. So, V out should be equal to 1 by 10 multiplied by 1 by 10 times V in, right. Apparently, it is so. All these resistances are equal. Here also all these resistances are equal. Okay. But the question is, will it really be so? Think of it for a moment, and you can pause the video at this point, think of it and then come back and see is it really so or not. And I am saying this is really not equal to. Why? Because so this circuit, so let us do some circuit simplification. Okay. So, circuit some circuit simplification will give it like, so I have 9 R here and then 1 R this is V in, this is this part, and from here I take the output to the input of the second stage. Again I have 9 R here and 1 R here. So, I write them as like this, 9 R and R. So, this is V out with respect to this point. Okay. This is V in and V out is between these two terminals. Now, let us calculate how much is V out. So, let us calculate it directly. So, if we do a direct calculation, then this R and this 2, 9R and R. So, these two are in series, 9R and R, these two are in series, and this R is in parallel with that. So, we can write V out is equal to V in. So, this will be multiplied by this combination R parallel 10R, R parallel 10R whole divided by R parallel 10R, that means this part, plus 9R. Okay. And so, this will be the potential difference between these 2 points or these 2 points, same. And then let us multiply it once again by another factor, which will be R divided by R plus 9R. Okay. So, this becomes whole multiplied by V in. Oh, V in is already written. So, then this becomes V in. Now, R 10R, this is same as 10 by 11 R. Okay. So, R parallel 10 R. So, that will be 10 by 11. Below we will have also 10 by 11 plus 9. And this is 1 over 10. Okay. So, then this becomes how much? Okay. This R you can cancel. So, we have V in into, so this 10 you can cancel, V in by 11, and there is one more factor, 1 over 10 plus 9 into 11, 10 plus 99, which is 109 divided by 11. So, this I am writing above. So, this is V in by 109, not equal to V in by 100. Please check my calculation. If I have done any mistake, please point it out, correct it yourself, it is not difficult, but the conclusion is this V out is not 1 over 100 equal to V in. So, this is the observation. And why is it so? Actually, this is because, so if we think that this V out, call this V out prime intermediate, if we think this equal to 1 over 10 as V in, that is only true if there is no current flowing through this or through this. So, V out prime will be equal to V in by 10 only if this current I, or here only if I is equal to 0. If there is a current, we call that a loading effect, then this relationship is not true. Okay. Once again, this potential divider rule is only true if no current is flowing out. That's very basic. Okay. And if some current is flowing out, then basically this this resistance will be in parallel with something else. So, its true value will be smaller than just R, because there is a parallel resistance which is this. So, the potential that we will have here actually is less than this expected value. If I is not equal to 0, then V out prime will be less than V in by 10. Okay. And then okay, there is, if we assume there is no loading effect here, if we just have an ideal voltmeter or potentiometer connected here, so no current is flowing. So, this part will give 1 by 100, that is for sure. V out is equal, sorry, 1 by 10 of V out prime, assuming this current called I 1 equal to 0. That is possible if we have a ideal voltmeter here or a potentiometer here then. So, of course, then V out will be less than V in by 100. That is what we have seen, it is less than V in by 100, it is according to my calculation V in by 109. Check my calculation please. So, what is the solution? So, now we are going to see a new circuit which is called Kelvin-Varley potential divider, where the previous problem will not exist. What was the problem? The problem was due to the loading effect of the first stage by the second stage. The second stage of this potential divider is drawing some current I, and therefore, the output from the first stage is not as expected, it is less than the expected value. Okay. So, let me first also write the problem. The problem of in the above circuit is that the second stage loads the first stage, which means the second stage draws current from the first stage. Therefore, output of first stage is less than the expected value. Okay, expected value, I think you understand. In the previous case, expected value was 1 over 10, but the actual value was less than that. Okay. Now, the solution to this problem is a small modification, but very nice and well thought of modification of the previous circuit. What is the modification? The modification is like this. So, I will first take say 10 resistances 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I will take a extra one. Why? I will tell later. 11. Okay. So, this is, let me put the counts 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 resistances. Okay. In the first stage, so this is first stage, there is an extra one. So, note this extra resistance, and all these resistances are equal, of course. So, their value you can take as R, 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 R and R all equal. Now, in the second stage, I will take only 10 resistances. This extra one is not required. Now, what I will do is, so you know the input will of course be at the first stage. So, this is the input V in, and here there will be a nice trick. The trick is like this. So, we will have two jockeys instead of one, and these two jockeys will be mechanically coupled. So, these two move together. Okay. So, this is mechanical coupling. So, these two pointers move together. If this pointer is connected here, the next pointer will be connected to the switch after leaving one switch. Okay. So, these two will be always across two resistances. Okay. So, you cannot move them individually, you have to move it together only, and they will always connect in parallel to two resistances always. And now, the next thing what I will do is, so call these resistances as okay, if this is R 1 1 1 1 for stage 1, call this R 2, all these are equal of course, but not necessarily equal to R 1. So, I will choose this total resistance of stage 2, which is 10 R 2 equal to two resistances of first stage. Okay. So, this is total resistance of second stage, and this is resistance of two resistances of stage 1. Okay. So, I will choose it in this way. So, that means I will choose R 2 equal to 2 by 10 R 1, which is R 1 by 5. So, let us choose it this way, R 1 by 5 equal to R 1 by 5, and so on. This is also R 1 by 5. If I do this, and then the output I will take from this point as the reference, call this reference point. So, output will be taken from this reference point, and so between this reference point and one point. So, this you can move, you can connect it anywhere to this second stage. So, between these 2 points I will take V out. Okay. So, the trick is this, the main trick is here, that this mechanical coupling, this moves together, and the second trick is the choice of these resistances. Okay. So, I have chosen 2 R 1 same as this 10 R 2. Now, how does this help? Now the total resistance in the first stage, or total equivalent resistance, is how much? R1 times 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. Then 7, 8. So 8 and 9. 9 R1 plus this and this in parallel. Okay. So the equivalent resistance of first stage will be 9 R1, 1, 2, 3, 4, 5, 6, 7, 8, 9 plus this 2 R1, 2 R1 parallel this. This is 10 R2. And I have cleverly chosen this 2 R1 equal to 10 R2 here. 2 R1 is same as 10 R2. So this is nothing but 9 R1 plus 2 R1, and this is also 2 R1. So this becomes 9 R1 plus 2 R1 parallel 2 R1 is R1 only. This is 10 R1. So equivalent resistance of this part is 10 R1 only. Okay. Now if the lower pointer, okay, call this okay, P1, P2 and this P3. Okay, P1 is the position of the lower pointer, which is in this case 3. Okay, so P1 is the position of this pointer. Okay, is equal to 3 in this diagram. And P3 is equal to 1, 2, 3. Okay, again 3. Okay, let's change it. One, 2, 3, 4 in this diagram. Okay. Now, what will be the value of V out? That's the question. Now, V out is equal to how much? We can write, okay, if we call this voltage as V out prime, then this is of course V out prime multiplied by this factor 1, 2, 3, 4 by 10. Okay. So, V out prime multiplied by, in this case, 4 by 10. Or in general, this is V out prime multiplied by the P3 by 10. This is V out prime. Now, how much is V out prime? This will be the voltage drop across these two terminals. Okay. So, V out prime is therefore V in total voltage divided by this total resistance. Total resistance is how much? Is this 9 R1 plus 2 R1 parallel 2 R1, or we can write first 10 R2. This is V in divided by this and multiplied by the resistance here, equivalent resistance between these two terminals, okay, which is this plus this. So, 2 R1, not plus, parallel. Okay. So, then this comes out to be V in, and this is now 2 R1 is same as again see this calculation, same as 10 R2. So this will come out to be R1 only, V1 R1 whole divided by, this is again R1 plus 9 R1, 10 R1. So this is 1 over 10, V in by 10. Okay, so V out prime is V in by 10, and okay, then I have made a small mistake. Okay, so let me first call this potential. So I have made a small mistake in here. So let me call this potential V out double prime. Okay, and this should be V out double prime. Okay. So V out double prime is this voltage V out prime multiplied by this 4 by 10. Okay, so this was not V out. Okay. That's first stage. This is second stage. Okay. So now how much is V out? V out will be okay, let's have another notation. Call this potential here to here, okay, here to here, V out triple prime 1 2 3. So this is V out will be then this put. So let's start from here, 0 to this point, V out 3, V out triple prime, and then so this is same as, now this point is same as this point, and from we have another voltage V out double prime. Okay, so now this, now V out 3, V out triple prime is same as V in multiplied by 1 2 3 R1 by the total equivalent resistance is of course 10 R1, because there are 11, but here this is actually equivalent to 1 resistance. There are 2, but there is another 2 here which equivalently is just 1 resistance. So therefore this part I can write as V in multiplied by 3 by 10, or in general P1, this P1 is the position of this point, this lower pointer. Okay, so divided by 10, and plus this we already have seen, V out so V out double prime is here, V out double prime is here, so let's write it, V out prime multiplied by P3 divided by 10. So from here, and then this will be equal to V in P1 by 10 plus, in place of V out prime, let's use this equation, V out prime is V in by 10. So V in by 10 multiplied by P3 by 10 into P3 by 10. So this is V in P1 by 10 plus V in P3 by 100. So that's so nice. So the output depends on this pointer, the lower pointer. This is important. This is not important in the final result. P1 and this P3. So now if we want say 0.01 volt, okay, so if we want V out equals 0.01 Vin, then we can set P1 equal to 0 and P3 equal to 1. If we set P1 equal to 0, this term goes away. P3 equal to 1 means it will be Vin by 100. So we will have the desired output. So we will bring this pointer down here at 0 level down. So this will automatically come together with it here. We will bring this pointer after the first resistance here. Okay. So, and now if you want say any other arbitrary value, so if we now want V out equals V in by say V in multiplied by 0.23, then set P1 equal to 2 and P3 equal to 3. So that means bring this pointer down here after 2 resistances and this pointer after 3 resistances, 1, 2, 3, bring it here. Okay. So this way you can get any decimal fraction of V in as the V out. And similarly, now if we say in this diagram, in this particular diagram, how much is V out? P1 is 1, 2, 3, P3 is 1, 2, 3, 4. So this is 3, this is 4. So therefore, in the above diagram, we have V out will be equal to 3 and 4. So 0.34, 0.34 V in. So you can get any decimal fraction of V in this way. Okay. So and now suppose you need to get a fraction decimal up to say up to 4 decimal places. Okay. So if we want V out equal to V in multiplied by say 0.3264, then what do we do? Can we get that from here? No. With 2 stages, we can get up to 2 decimal places. If we want to get up to 4 decimal places, we need 4 such stages. So let me draw the circuit, and this will be the end of today's class after I draw this circuit. Okay. And I request you, instead of seeing my drawing, you try it yourself. You stop the video here. This will be the last thing I will do. So, but I will request you, you do it yourself, try it yourself. If you need any help, continue with the video. So I copy this. Okay. So I already have 2 stages. So I will copy it once again so that I have 4 stages. And now I will do the editing here on top of it. So this is one stage, this is another stage, this is the third stage, and then I will have the fourth stage. So what I need 11 resistances in the first stage, but since now there is a third stage, I also need 11 resistance in the second stage as well. Okay, so we have 11 resistances both in first and second stage, and we have to ensure that this total resistance is same as these two resistances, and I am telling you that this total resistance is going to be same as 10 times R2, not 11 times R2, 10 times R2. Why? Hold on for a few minutes. This total resistance is going to be 10 R2, not 11 R2. So therefore, we want here R 10 R2 same as 2 R1, which means R2 is R1 by 5, like this. Okay, fine. So let me write it directly. R2 is R1 by 5. Okay. And these two are mechanically coupled together, so they move together. Here also in the third stage, we will have a mechanically coupled arrangement. So these two pointers move together. Okay, so you can move these two together, you cannot move them alone. Now once again, while choosing these resistances, I have to make sure, okay, call this R3. So these are R3. We have 11 of them, and then this last stage you call R4. Here we have 10 of them. Okay, call this R4. Okay. Now here we have 10 of them, and here we have 11, right? But so what we will want? We will want that this 10 is same as this 2, because this 2 and this 10 are parallel, and I want that this 2 and this 10 become equal, so that the effective value is same as not 2 R3 but only 1 R3. Okay. So here we will want that 10 R4 same as 2 R3. That means R4 will be R3 by 5. So you can write here R3 by 5, R3 by 5, so on, always. So therefore, now how much is the total resistance of third stage, total equivalent resistance? We have 11 of them, but these two are in parallel with another equivalent 2. So this 2 and this 2 becomes only 1. So actually this is equivalent to 10 resistances. This is equivalently 10 resistances. Okay, not 11, only 10. And then this 10 resistances, that means 10 R3 is coming in parallel to 2 R2. So we will again want that 2 R2 same as 10 R3, meaning R2 equal to or R3 equal to R2 by 5. So here you can then write this as R2 by 5, R2 by 5, so on. So therefore this will become, so R3 is R2 by 5, so this will become R2 by 25 and so on. Okay, and then the total equivalent resistance of this is 10 R3. This 10 R3 is coming in parallel with 2 R2. So then we want 2 R2 same as 10 R3. So R3 same as R2 by 5. Okay. So, oh, this I already have written. So here how much resistance do we have? This 2, and the parallel thing is equivalent to only 1 resistance. So although there are 11, actually it's equivalent to only 10. That's the key of this circuit. There is only 10 resistances, equivalent 10 resistances. This 2 and this everything together becomes only 1. Okay, so there, that means we have 10 R2 in total here, and this 10 R2 must come in parallel with 2 R1. So 2 R1 we want it to be 10 R2. So R2 therefore R1 by 5, which is already written here. Okay, so then this is R1 by 5, this is R2 by 5. So that means it will be actually R1 by 25. And then therefore this will be equal to actually R1 by 125 divided by 5 divided by 5 divided by 5. Okay. So this is how the resistances should be, and note we should have 11 resistance, 11 resistance, 11 resistance in first, second, third, in all stages except the last stage. The last stage should have only 10 resistances. Okay, this is another important fact. And now, okay, last thing, where is the output taken from? The output will be taken from this reference point. So this as the reference. So output will be taken between this reference and this final jockey. This has 2 jockeys mechanically coupled, this has 2 jockeys mechanically coupled. Similarly this, the last one has only 1 jockey. And the output is between this reference point, very important, between this reference point and here. This is the output. Okay. Now if we now in this configuration, according to what we have drawn, how much is V out? Okay. So to calculate V out, so we can do it like this. We have 1, 2, 3 resistances. So V out will be therefore 0.3, 1, 2, 3. Then here we have 1, 2, 3, 4. 4 up to the lower resistance. Okay. So 0.04, another 0.04 means 0.34. Then here we have 1, 2, 3 again. So 0.003, that means totally 0.343. Let me make it smaller, 0.343. And then finally here we have 1, 2, 3, 4. From the lowest point, 1, 2, 3, 4 resistances. So another 4. This times V in this diagram. Okay. Now what we actually wanted? We wanted 0.3264. If this is what we want, then we have to adjust these jockeys. Okay. This should be after 3. Okay, 1, 2, 3, fine. This should be after 2. So this point should come here. After 2 resistances. So let me bring this down exactly after 2 resistances. Okay, here. Like this. So we have 1, 2, 3, 3, 1, 2, 2 done. Then next is 0.006. So this should go therefore after 1, 2, 3, 4, 5, 6. It should come here. 1, 2, 3, 4, 5, 6. So we do it. One, 2, 3, 4, 5, 6. Fine. And okay. So we got 0.6 done. Then 4. That means this should come after 4. 1, 2, 3, 4. Okay, it's already there. So that's great. Okay. So then we actually now have what we wanted, 0.3264 times V in. So we are done. Thank you.